Hello, advanced physics students. This is Dr. Brenzy here, and this is lesson 7.2. And in this lesson, we're going to be talking about something that's called rotational inertia. We've heard the word inertia before in Unit 3, and we've had some discussion about what that means, and we're going to revisit that today. But now we're going to talk about it in the context of rotation as well. So we have this thing called rotational inertia. And we're going to be able to define what that rotational inertia is and explain its role in something that's rotating. And then we're going to be able to also calculate the rotational inertia of some basic shapes. Now, the concept behind this idea of rotational inertia is that there are some things that are harder to rotate than other things. So I took a couple of snapshots of a trebuchet, and if you imagine that this bucket is full of rocks or is full of kitty litter or something like that, and if I place that bucket here, you might imagine that it is relatively easy for me to, like, say, pick up the string right here and be able to rotate it up and down with relatively little trouble. But if I took that same bucket full of kitty litter or full of rocks and placed it way over here and then tried to pull up and down on the string to manipulate it, what hopefully you can visualize is that it's going to be a lot harder for me to pull or rotate this arm when this bucket is way out here, as opposed to when the bucket was very close to where the arm is rotating. And that's the idea behind rotational inertia. Now, going back to Unit 3 when we were talking about Newton's laws, we define this word inertia as an object's resistance to change in its motion. And since we were talking about motion along a straight line, we could call it linear motion. Now, what we remember is that inertia depends on an object's mass. So if I have two different boxes of two different masses, and I push on them with the same force, as I indicate with this red arrow here, one of these two boxes will experience a larger change in its motion than the other. Well, Newton defined change in motion as acceleration, so, I forgot that I was going to put the F's there. But this small box is going to experience a much larger acceleration than the larger box will. So it's a lot easier to change the motion of this small box than it is to change the motion of this more massive box. So mass has everything to do with the amount of inertia an object has in linear motion. Rotational inertia works in a similar manner. It's an object's resistance to change in its rotational inertia, or rotational motion, So if we're trying to rotate something, some things are harder to rotate than others. So if I have two rods or two boards, and I'm trying to rotate them around a pivot that is at the end of the board, this board right here, or this rod, I guess we could call it a rod, is going to be relatively easy to change its rotational motion as opposed to this rod over here. So if I place a force, the same force, at the same distance away from the pivot, which means I'm exerting the same amount of torque on both of these bars, this bar over here is going to change its rotational motion a lot more than this bar over here. And that's the idea of rotational inertia. So this bar has more rotational inertia than this bar here. Now, I want to point out to you that in some physics texts, as a matter of fact, in a lot of physics texts, you'll also hear this referred to as moment of inertia. And that's actually the word that I learned how to use when I was first introduced to rotational motion. So those two can be used interchangeably. They mean the exact same thing. And very often you'll hear me flip back and forth between the two. They mean the exact same thing. So what does this rotational inertia depend on? What are the factors that affect rotational inertia? First of all, the object's mass. Because if you have more mass, you have more rotational inertia. So if I were to draw two boxes on a string, and I'm trying to rotate these strings around these pivots, right here and here, you could imagine that I would have to exert less torque to get this one to change its rotational motion, as opposed to this one, which will have a harder time starting up its motion. So this one has what's called small rotational inertia, or a small moment of inertia. And in physics, we give rotational inertia the variable I, capital I. So you're going to be seeing that a lot in this unit. As opposed to this one, which is going to have a large moment of inertia. And again, that variable is capital I. So that's one factor that affects the rotational inertia of an object. Another factor that affects rotational inertia is how far the object is away from the pivot point. The larger distance or larger radius it has from the pivot point, the more rotational inertia it has, the harder it is to change that object's rotational motion. So if I now have two boxes that have the same mass, but one of them is at a much larger distance away from the pivot point, it's going to be a lot harder for me to change this box's rotational motion compared to this box's rotational motion because it is closer to the pivot point. So this one will have a small moment of inertia. This one, because it's farther away, will have a much larger moment of inertia. So is there some sort of like number that we can attach to this? Just like with inertia back in Unit 3, we found out that the amount of mass something has is its amount of inertia. Well, yes, there is actually. And what we do in physics is we have this formula right here. So if you have a small mass, m, located at a distance r away from where you're trying to pivot, so this is, let's say that this is where we're trying to pivot around, and this mass is located at a distance r, we can calculate this mass's moment of inertia by using this formula here. I is equal to m times r squared. Remember, moment of inertia or rotational inertia depends on the object's mass and how far that object is away from the pivot. And if you multiply mass times distance squared, you are multiplying kilograms times meters squared, and that is the units that we use with moment of inertia. So kilograms meters squared are the units that we use for rotational inertia. Now in physics we can actually find the rotational inertia of rigid objects. These are objects that have a certain size and shape, and we can calculate their rotational inertia as well. So if you have, like, say, a solid cylinder, so let's say a can of pop or a can of soda, however you like to say it, and you were trying to spin that around its center axis, so imagine that this is going through the center of the Coke can or Pepsi can or whatever you like to drink, and you're trying to spin that can that's full of liquid. Its moment of inertia, you could actually use this formula to calculate its moment of inertia and figure out how hard it is to rotate. You can also calculate the rotational inertia of hoops and rods and all sorts of other different shapes. Now, I'm not going to expect you to memorize the formulas of these different objects. I am actually going to give you a sheet that you can use to look those up, but we are going to have to become pretty good at looking them up. And one of the tricky things about looking them up is that not only does moment of inertia depend on the shape of the object, but it also depends on where the axis of rotation is, so this red line, because one of the other formulas you're going to get on your sheet is something that looks like this. Now, the only difference between this and this is where the axis of rotation is located. So you have to be careful about that. In this case, we are spinning a rod around its center, but here we are spinning a rod around one of its ends. And notice that they have two completely different formulas. Well, I shouldn't say completely different, but this one is 1/12 ml squared. This one is 1/3 ml squared. So you have to be careful when you're looking these up. You have to know not only what shape is rotating, but you also have to know where that axis of rotation is. So rotational inertia depends on the shape and where the axis is located. So be careful about that when you're looking up rotational inertia for these shapes. All right, so let's go through a couple of examples right now. First of all, let's start off with calculating the moment of inertia of three balls that are on what we'll assume is a massless rod. So imagine this being a rod, and we're spinning that rod around this axis of rotation here. And we're only going to worry about the mass of these individual three balls here. We're not going to worry about the moment of inertia of the rod that's connecting the three. So what I do is, just like with mass, you can add masses together to get a total mass. So we can add the moment of inertia of each of these three balls together to get the total moment of inertia. So when I have an object that's a distance r away from the pivot point, or the axis of rotation, I can use this formula, I equals mr squared, for each of these three objects. So let's give each of these a label. I'll call the far left one A, then the middle one B, and then the far right one C. And we'll calculate their moment of inertia separately and then add them all together to get the total moment of inertia. All right, so for object A, we're going to use the formula for a single mass located at a distance r away from the pivot. And it's a mass of 2 kilograms. And it is located 2 meters away from the pivot. So when I multiply 2 times 2 squared, I get 8. So that has a moment of inertia of 8 kilograms meters squared. Going on to object B, same formula, but this time it has a mass of 1 kilogram. It's a distance of 2 meters away from the pivot point, or the axis of rotation. And its moment of inertia then is going to be 4 kilogram meters squared. This third object, it has a mass of 3 kilograms. Now be careful here, because notice that remember that r is the distance from the object all the way over to the pivot. You might be very tempted to put 1 in here. So you might be tempted to say 3 times 1 squared, but that's not what I need to put in here. I actually need to figure out its total distance to the axis. And that ends up being 2 plus 1, which is 3. So don't just plug and chug numbers in from the diagram. Make sure that what you're plugging in here is actually the distance that object is away from the axis of rotation. Okay, so now that I've carefully looked at that, I plug those numbers in and I calculate 27 kilograms meters squared. So the total rotational inertia of these three objects put together is the sum of their individual rotational inertias So 8 plus 4 plus 27, and I get 39 kilograms meters squared. Okay, now let me do one more quick example. And let me actually look at a rigid object, a rigid body. And so let's look at a thin rod. Has a mass of 6 kilograms and a length of 5 meters, and it's being rotated around one of its ends. So if I'm only given this information up here, what I'm going to do is I'm going to look at my reference sheet for moments of inertia, and I'm going to be looking for a thin rod that is rotated around one of its ends, and I'm going to be looking for this picture right here. So that's the picture I would look up. This axis of rotation is at the end of the rod, so that's the one I want. And so its moment of inertia is ml squared divided by 3. So I'm going to write that formula down. And then all I have to do is plug in the mass of the rod and its length. And when I evaluate that expression, I'm going to get 50 kilogram meters squared. So the trickiest part about using this or finding the moment of inertia of rigid bodies is actually figuring out which formula do I use. Okay, because this rod's being rotated around one end, I actually use the formula for a thin rod rotated around an end. And that's going to be ml squared over 3. Okay, team, well, that's all I have about moment of inertia or rotational inertia. And when we get to class, we're going to have an opportunity to practice looking these up and looking up the right formula. And then we'll have some practice actually calculating moments of inertia. All right, I look forward to seeing you in class, and have a good one. Bye.